Okay, so we are going to uh, learn about something called the constant rate of change. So read along with me on your paper. Relationships that have straight line graphs are called linear relationships. Okay, where you've heard linear before is in the last unit, if you had an equation that made a line, it was a linear equation. So now we're looking at relationships. If there's a relationship between something, and if you were to graph that relationship, it makes a line, that's a linear relationship. So underline that word, linear relationship. Now there's something called the rate of change. So the rate of change between any 2 points in a linear relationship is the same or constant. When we say constant, we mean like something in your life that's constant. It's constantly happening. Okay, like consistency. That's the kind of constant we're looking at. So the rate of change, so underline that. The rate of change between any 2 points in a linear relationship is the same. So if you look at a relationship, if you pick 2 points and you find the rate of change, it would be the same as 2 other points. And we'll see examples of all of this. And finally, a linear relationship has a constant rate of change. So that rate of change, that linear relationship that we looked at, because the rate is the same, we call it constant rate of change. And that's what we'll be studying today, are relationships that have a constant rate of change. It's basically like having a pattern. Okay, let's look at our first example. Camille can download 3 songs from the internet each minute. This is shown in the table below. So here's our time in minutes, and this should say songs. So time in minutes and number of songs. So just to make sense of this table a little bit, 0, 0 is the start. When she turns her computer on to download her songs, she has none. So when the time is 0 minutes, so this is the beginning, she has no songs. At 1 minute, she has 3 songs. 2 minutes, 6 songs. 3 minutes, 9 songs. And 4 minutes, 2 songs. Okay. Now you may be noticing that, 1 times 3 is 3. 2 times 3 is 6. 3 times 3 is 9. And there is a pattern there. But that's not the pattern I want you to look at. And that's not the pattern that we use for a constant rate of change. What we want to look at is we want to look at how our values change within a row. Think of it like this. If we had a table of values, usually the first value is our x, the second value is our y. We can assume that. So what we're going to do is, if we were to graph this, because remember we're looking at linear relationships, so this could actually create lines. We have an x value and a y value. I could take this and make ordered pairs if I wanted to. Okay, eventually we will. But the important thing about that is when we're looking for this rate of change, we're looking to see how our x values change and how the y values change. So what you'll notice on your paper is there are some arrows going from one x value to the next. And we want to compare we want to look at what the pattern is. Compare and see what happens. Added 1, add 1, add 1, add 1. So this pattern that we look at is actually within a row or a column here. So I'm not worried about how the x becomes y. I'm more worried about how the x's change and how the y's change. My x's change, they go up by 1. My y change is up by 3. So each time the x goes up by 1, my y goes up by 3. Now, something that's very important to pay attention to. The rate of change is 3 songs per minute. It's very similar to a unit rate. You won't always get a unit rate, but usually when you have something where it's per mile, per minute, per day, you usually end up wanting to get a unit rate. What I want you to notice about this unit rate is it's 3 over 1. Let's look at our pattern. The pattern of my y's went up by 3s. The pattern of my x's went up by 1s. So what's happening is my numerator is showing how the y values change. The denominator is showing how the x values change. So what I want you to add to your paper is change in y over change in x. This is something that's going to repeat itself or show up over and over and over again for the next few months, and then again in high school. This is a very important piece in the pre-algebra and algebra puzzle. Very important. Make sure you find a spot to add that on your paper. Change in y over change in x. And if we look at this, we're just seeing how are the y's changing. The y's are changing by positive 3. How are my x's changing? Positive 1. You could draw these arrows, and you probably will, but this is something important to start getting in your head. Okay, let's look at another example. Use the table to determine the relationship between degrees Fahrenheit and degrees Celsius. Is it linear? Oh, I need to back up a second. Oh, I don't. I'm sorry. I thought we were asking if it was linear on the last one, but we're not. Okay, sorry about that. Use the table to determine if the relationship between degrees Fahrenheit and degrees Celsius is linear. Add a note on the side of your paper. If there is a constant rate of change, it is linear. If there is a constant rate of change, it is linear. Lines have a pattern. If the line doesn't have a pattern, that's when you start getting zigzags and weird shaped things. The lines that we're looking at are straight. I don't mean horizontal or vertical, I mean they just don't curve or bend. And if the rate of change is constant, the ordered pairs will create a perfectly straight line. And we'll see a little more of that later. But for now, just trust that if there's a constant rate of change, it is linear. And we're going to do a bunch of examples, so this should make sense as we go. So the first thing to do, determine our pattern. How are the y's changing? How are the x's changing? We can assume that our first column are the x's, second column are the y's. So make sure you label the x and the y. So let's see how, remember, it's change in y over change in X. In our case, it's change in the Fahrenheit over change in the Celsius. Let's see how our Y's change. Well, 32 going up to 41, that's adding 9. 41 up to 50 is adding 9. Now double check that it actually works. Don't get in a habit of just getting the first change and then copying it down. It's not automatically going to create a pattern. Be very careful. So my change in the Y's, or the Fahrenheit, is positive 9. If my numbers were getting smaller, it would be a negative. Degrees Celsius, it's increasing by 5. So my denominator is 5. So this is one of the few times that we go out of order with the alphabet, because my Y values are in the numerator and my X value, the change, is in the denominator. Now, because we have a pattern, that means we have a constant rate of change. So yes, it is linear. Let's look at the next one. Use the table to determine the cooling of water if it represents a linear relationship. So again, we're looking for change in Y over the change in X. And if you look at your worksheet, they actually put some numbers into a subtraction problem. We're going to do this the way we did the last one. We'll come back to subtraction later. On your worksheet, I want you to label the X and the Y, and I want you to find the pattern. We'll use these little arrow symbols. So we're going to find our change in Y first. Uh-oh. Something didn't transfer over. Let's fix this really quick. Okay, that's better. So now my table matches your paper. So we don't have one up here. Okay, so let's look at our pattern. 95 to 90 is down 5. 90 to 86 is down 4. 86 to 82 is down 4. Let's look at these. 5 to 10, up 5, up 5, up 5. So my change in Y is not consistent. Okay, I have different changes. There is no pattern. So I can't really do this because the Y's have no pattern. Okay, and when I say pattern, if it said 5, 4, 3, that doesn't count. It needs to be the same thing happening each row to row. Kind of like on the left-hand side, it goes up by 5 every time. I would need the right-hand side to either go down by 4 every time, go down by 5. Each change has to be consistent on each side. So this is not linear because there's no constant rate of change. So circle that answer on that paper. Okay, let's look at the next one. The altitude of a certain airplane already in the air is shown after a few minutes in the table below. Is the relationship linear? If so, find the constant rate of change. So first thing we'll do, we have this is our X, this is our Y. Let's see if we have a pattern. Up by 2, up by 2, up by 2. Looks good. Next, down by 500. Down by 500. down by 500. And if you notice, what I'm doing is I'm subtracting 3,000 minus 3,500. Kind of working backwards a little bit. So keep that in mind, that if you need to grab a calculator to figure out the differences, you can. So I have a constant rate of change because I have a pattern for the x's and I have a pattern for the y's. So yes, it is linear. And the rate of change is our change in y over the change in x. We could actually simplify that down into negative 250 over 1. Now, when you write rate of change, you do want to put it in terms of the situation. So our y's are on top and our x's are on the bottom. So the top number is altitude, the bottom number is minutes. So this would be negative 250 feet per minute. So that's where the words come in. It's basically like having that unit rate. If you remember that our y's are on top, our change in y is on top, change in x is on the bottom, then you can refer back and see how to write that as your constant rate of change. Let's look at another example. So for the next 4 examples, we're going to decide if the relationship is linear, and if it is linear, get the constant rate of change. So off to the side, you may want to make a little note. Change in y over change in x. Okay, remember our first column will be x's, second column y's. Okay, so we want to look at our patterns. If there is one, so 15 to 30, up 15, up 15, up 15. And our x's, up 5, up 5, up 5. I have a pattern for each, so we know it's linear. And then we find the constant rate of change. Change in y. How are the y values changing? Well, by 15. X values are changing by 5. And when we look at our information, it's cost over time, right? It's cents per hour. That's a cent sign, sorry. So when I simplify this, I get 3 cents per hour. That's how you would typically write your rate of change. The bare minimum, you got to have this guy. Let's look at number 2. 2 gets a little crazy because we see fractions. But it's not that bad. Oops, this is supposed to be 3 over 2. Okay. So we're going to take a look at our pattern. Plus 2, plus 2, plus 2. Now down here, gets a little crazy because we have fractions. But it's not that bad. With fractions, it's hard to compare, or you can't add or subtract if you don't have common denominators. So let's make everything in terms of fourths. Okay. Oh, I'm sorry. This is 1 1/2. So 1 1/2. Let's make that improper. 3 over 2. Now let's give that a denominator of 4. So we're going to make this say 6/4. This guy here, let's convert it to improper, 9/4. And then 3/1, let's put that into fourths. Now I can see if there's a pattern because I'm going by fourths. So what I can see here is 3/4 up to 6/4. Well, what plus 3/4 would equal 6/4? 3/4. Okay, next one. What plus 6/4 is going to get me to 9/4? Plus 3/4. What plus 9/4 will get me to 12/4? 3/4. So I do have a pattern. So yes, this is linear, and my constant rate of change would be change in y over change in x. Honestly, if you got to this point, you can go ahead and say 3/4 cup of vinegar. You know what? If you got to this point, you can make that your answer. I'm happy. I'm not too stressed about dealing with the fractions. Go ahead and skip the third one. We can come back to decimals another time. Let's go to 4. So again, for number 4, we're going to determine the change in y over the change in x. So we definitely want to count and see if we have a pattern. 35 to 56. Now, I'll tell you, you might need a calculator here. But on a side note, my x values are going to be much easier to see if there's a pattern. I'm going to start there just to see, because it doesn't look right over here. Now 8 to 10 is plus 2, 10 to 20 is plus 10. There is no pattern here. Since these are not the same, not linear. And again, if you were to create ordered pairs and graph them, you would have a zigzag line. Would not be pretty. The last thing we're going to look at is the matching the table. We're going to do the first one together, and then you'll do the rest on your own. So it just says match the table with the rate of change. So we know these are all linear. Okay, so we just have to find the change. Remember, it's change in y or change in x. So let's look at our y's. First, my change in y. Now there's not a lot of room, so I'm not going to do a bunch of crazy work underneath, but I can see visually that it's going up by 15 feet, right? And then my time is going up by 1. 15 feet per minute. So those two match up. Okay, let's go ahead and pause. And I want you to try the rest of these 3 on your own.